Okay, gang, our next series here on the key concepts review is going to be on sections 2.2 to 2.3. So we're not quite into actual calculus yet, but we are looking at some behavior models. So let's go ahead and check it out. So for each pair of graphs shown, determine whether g of x appears to be the right end behavior model for f of x, a left end model for f of x, or neither or both. So g of x is the right end behavior of f of x if g is the left end behavior of f of x, or neither. So basically we're seeing if the left sides and the right sides kind of match up. And if you take a look at question 1, on the left side, we're asymptotic at y equals -1. And over here, we're also asymptotic at y equals -1. So yeah, these share the same left end behavior. Right end behavior, again, these are both asymptotic at y equals -1. So left and right behavior models are the same. Let's take a look at number 2. On the left side, this looks as though it's hard to see, but it looks like it's going to slowly increase, whereas this one looks like it's going to decrease. So I'd say the left's behavior models are not the same. Over here, this on the right side, this is also decreasing, but on the left side, we're looking on the right side of g of x, we're increasing. So really, none of the behavior models are matching here. Where one is increasing, the other one's decreasing, and where with the other one's decreasing, the other side is increasing. So neither of these really match up. So behavior model going to the same infinity, asymptotic at the same place, what have you. Moving on to question 3. Let's take a look at the left side. The left side, this appears to be growing more and more in amplitude. So it doesn't really approach a limit on the left side, whereas the left side of g of x clearly approaches a limit of y equals 1. So the left side do not have the same behavior model. The right side, however, if you take a look at f of x, this is settling down at x equals 1. It's oscillating around y equals 1, but it is settling at y equals 1, and g of x is already at y equals 1. So the right end behavior model is the same for both of those. Let's take a look at number 4 then. On the left side, we notice that we are, well, it's linear, so it is approaching that slant asymptote. And g of x is also approaching that same slant asymptote. So the left's behavior model is the same. They are approaching that slanted direction. On the right side, however, you look at f of x is decreasing. However, g of x is increasing. So those are kind of opposite behavior models. So the right sides do not match. That was pretty easy, right? How about here? Determine whether the function represents are continuous at x equals c. If it is not continuous, identify the point of discontinuity. So here, can I pass through c without picking up my pencil? Yes, I can. So that means this is continuous. This is continuous. Over here, can I pass through C without picking up my pencil? And the answer is no, because there is a hole here. So this is a hole. Discontinuous. Over here, there's still a hole here. And C is defined but not defined at where the y-coordinate is the same as the y-coordinate of the hole again. So this is another discontinuity. So this is, yeah, just another hole or break. D, clearly we have to pick up our pencil to go from the left side to the right side. So this is discontinuous. And this one we call a break, because it looks as though the function did match and then one of them broke off of the other. So this is a break. Letter E, not continuous. Clearly you'd have to pick up your pencil to get from the right side of the left half to get to the left side of the right half. Well, that's a lot to go. And this is asymptotic. As we approach C from the left side, the function goes to negative infinity. So this is discontinuous as well. This is an asymptote, or at least it's an asymptote on one side. And then this is an asymptote on both sides. So this is discontinuous, also an asymptote. Which I probably spelled incorrectly, but what do you do? Okay, can you think of an example of a function that has only one point of discontinuity? Let's see. Well, we can easily make a whole function. This is how I do it for all of my Algebra A kids. I start with a function like this, x plus 2, x minus 1 over the place where I want that whole to be. And then I expand that numerator, x squared plus x minus 2 on top of x minus 1. So this has one point of discontinuity. It is a whole when x equals positive 1. 2 points of discontinuity, you're going to do pretty much the same thing. Let's do this. X minus 5, x, and then x plus 5. And let's give this two wholes at x equals 5, and let's do x equals 0. Expand that, and you get, what is this, x cubed minus 25x over x squared minus 5x. That's going to have 2 points of discontinuity. You could use any coordinate you want. I should have mentioned that for letter A too. You don't have to have your discontinuity at x equals 1. How about an infinite number of points of discontinuity? What does that even look like? Infinite number. Well, I can think of one. What about y equals tangent x? Okay. Sure, that's always discontinuous at odd values of pi over 2, odd multiples of pi over 2, and there's an infinite number of them. So there's an infinite number of discontinuities. We only just get to see a few of them on any graphing window, but they go on because the tangent function goes on from negative infinity to positive infinity, with an exception of those wholes. Okay, how about a function that's continuous at every point? You can be very uncreative here. Y equals x. That's definitely continuous at every point. Or you can be a little more exotic. Maybe you want to do y equals sine x. It's a little bit more exotic, I think. How about discontinuous at every point? What does that even look like? I don't think you can make a function that's discontinuous at every point. And that is a lot different than what we're saying in question C for number 6. It's not the same thing. This one says that we have points of continuity. It's just that we have an infinite number of discontinuities. This one is saying we have no place where the function is continuous, So the function doesn't exist at all in essence. I mean, I don't know. I suppose you could do something weird like y equals negative x squared square root. There is no value of x that you can substitute into that function that will give you a y coordinate. So I suppose you could say that that is discontinuous at every point. So I think that's everything here, folks. This was a nice short one. After those first two went on forever, I was losing a little bit of hope. So that's your little bit of calculus review for today. Just a quick review on continuity and the different types of continuity. Of course, there's also asymptotes that go along with that. So I'll see you next time.